Next, we're going to look at a lemma that we'll need to prove a theorem shortly. This lemma says that if the sequence an converges to the real number a, it does converge to the real number a, if and only if, and before I continue, I'm going to remind us what that means. That's a two-directional proof. So let me start over. An converges to the real number a, if and only if each neighborhood of that limit a contains all but a finite number of terms of the sequence an. All right, well, just to start things off, my case one is going to be proving that this implies the second part. In other words, if an converges to a, then each neighborhood of a contains all but a finite terms of the sequence. Okay, so we're supposing that an converges to a. We're making that assumption. And let capital S be a neighborhood of a. All right, well now let's let epsilon greater than 0 be such that the interval a minus epsilon to a plus epsilon is completely contained in S. That's based upon strictly using the definition of what it means to be a neighborhood. Frequently, and in the future, I may start off when I need a neighborhood of capital A, I may just start off with an epsilon neighborhood. These are just nicer to work with. They're symmetric. A is in the middle of that interval, and so on. Okay, so now we have what we sometimes call an epsilon neighborhood of A. Now, since an converges to A, there's a capital N in the natural numbers such that n greater than or equal to that capital N implies an minus a is less than epsilon. That is simply using the definition of what it means for an to converge to a. For whatever epsilon we're given, there exists a capital N that makes this true whenever n is bigger than or equal to that capital N. All right, well, notice what this means. Maybe I'm going to put it in parentheses. Another way of writing this is that an is in the interval a minus epsilon to a plus epsilon. So this right here is the same thing as saying that. Those are equivalent statements. Okay, so for all n greater than capital N, an is in this interval. So it follows, thus I'll say, at most, the terms a1, a2, all the way up to a capital N minus 1 are not in capital S. And this is a finite number. Anytime you can write them out, indexed by 1, 2 to some integer, that means it's a finite set. From a capital N on, they're all in this neighborhood. Okay, I'm going to have to write a little bit smaller to get the other direction going. All right, so now I'm going to assume that each neighborhood of A contains all but a finite number of the terms of an. So, let's see, I'm going to have to prove this, so I'm going to need an epsilon. We're proving a limit. So let epsilon greater than 0. Sometimes I write let it be given, or sometimes I'll say choose epsilon greater than 0. All right, so what I need in this case is let epsilon greater than 0 be such that A, capital A minus epsilon, capital A plus epsilon, that interval contains all but a finite number of terms of the sequence AN. Okay, let that be such that that's my neighborhood of A, the epsilon neighborhood of A. Let that be such that, being repetitive here, such that it contains all but a finite number of terms. Of the sequence AN. Okay, so it's a finite, only a finite number of terms are not in that interval. Let's just let capital M, a natural number, be the largest index. Oops, largest index, such that A subcapital M is not in the interval. A minus epsilon to A plus epsilon. And what that means, I'll put in brackets, another way of writing this, is that so the collection of elements A, M plus 1, little a, M plus 1, little a, M plus 2, ... is all contained in A minus epsilon to A plus epsilon. Sorry, getting a little bit messy there. So from M plus 1 on, and let's see, am I off by 1? AM is not in that interval. So from AM plus 1 on, it is in that interval. So to finish this up, thus, n greater than capital M, or I could have said greater than or equal to capital M plus 1, implies that AN is an element of A minus epsilon, A plus epsilon, or in other words, AN minus A in absolute values is less than epsilon, and that completes the proof. That's the end of the proof. For whatever epsilon is chosen, we found a capital N, although this time we named it capital M, such that whenever n is bigger than that capital M, the distance between AN and A is less than epsilon. That completes the proof.